Hello everyone, my name is Taehoon Kim. The title of my presentation is Study on DID and CP-ABE-based Self-Sovereign Identity of Smart Vehicles. Let's start the presentation. The index is as follows. First, in the introduction, I will be explain the background and necessity of the proposed scheme. And later work, I will be explain the main scheme. And then I will be explain the proposed scheme and compare and analyze them. And I will conclude with the conclusion. First, let's start with the introduction. When user A and B exchange data, uh, they may be attacked by an attacker such as data leakage. Users must perform information security to protect their data. Among those, this study has carried out research on information authentication. What is authentication? Authentication is when user A proves their identity to user B. The procedure of authentication is as follows. First, the holder requests service from the issuer, the verifier, and the verifier requests data from the holder for service. And then the holder sends request data to the verifier. Finally, the verifier verifies, receives data, and provides service. However, existing centralized systems have privacy invasion issue. To address this issue, the decentralized system like DID is required. For this reason, authentication should be provided in a decentralized system. The difference between existing centralized system and the decentralized system is that the VDR is decentralized, and anyone can easily access and verifiable authenticate users. One of the scheme based on this is DID. DID is an extension of decentralized system. Next, I'd like to introduce DID. The various schemes developed to archive this. DID refers to a new type of identifier that enables verifiable and decentralized digital IDs. It is designed to be separated from centralized registries, ID providers, and certification authorities. Unlike traditional centralized system approach, it ensures self-sovereignty. This is the procedure of DID. The procedure is as follows. First, the holder generates a public key pairs and generate to DID value using public key as input. Then the holder binds DID and public key to generate a DID document, and it records it in the video. Second, the holder requests the VC issuance from the issuer, and then the issuer receives a DDO in the VDR from the VDR and verifies DDO. The issuer receives the DDO, the VDR, to authenticate the holder's DID and signature and verifies the signature through the public key in the DDO. Thirdly, if the signature is correct, the issuer issues a VC to the holder. Next, the holder generates a VP using the issued VC and submit it to the verifier. Finally, the verifier verifies the signature of holder and issuer in the VP and provides service to the holder if they are correct. Therefore, DID provides self-sovereign identity and removes dependence on centralized system. The following is a procedure of DID applied to smart vehicles. The holder is vehicle and the verifier is vehicle repair shop or RSU. However, if the verifier needs additional data such as a driver's license, and how can holder and verifier communicate securely? The following encryption scheme can be used. What is CP-ABE? CP-ABE is encryption scheme using data and attributes-based access structure. The verifier must have the appropriate attributes for the access structure of ciphertext to decrypt it. The advantage of CP-ABE are as follows. First, the holder can select access to their information. Second, the holder and verifier can communicate securely. Therefore, DID and CP-ABE are used in smart vehicles to provide self-sovereign identity. In summary, DID ensures self-sovereign identity and the removal of dependence on centralization and distributed data storage. Therefore, DID provides privacy. Also, CP-ABE ensures self-sovereignty and provides number of ciphertexts and storage efficiency. The following is an analysis table comparing late work as follows. This is our contributions. First, the VDR can verify whether the holder has approved the verifier. Second, it prevents revoked verifier cannot access the holder's data. Finally, the proposed scheme can output a constant size ciphertext regardless of the number of attributes. And therefore, the storage overhead of the VDR is reduced. This is the system parameters. First, there are participant entities. It means the holder, issuer, and verifier collectively. And DID and DDO are participants, DID and DID document. And EVCH is holders verifiable data credentials. And AVCV is verifiers attribute credentials. This is system entities. System entities are as follows. First, the holder as a vehicle is the subject of DID. The holder receives a VC from the issuer and creates a VP. Second, the issuer is a TTP such as an institution or company. The issuer creates a VC using the holder's claim and issues it to the verifier. Thirdly, the verifier is a service provider such as a service center. The verifier verifies the VP and access the holder's big data. Lastly, the VDR is built on-chain. This is the overall scenario. The proposed scheme is divided into 6 pages. First, in setting phase, participants generate system parameters and DID and public key pairs. And then participants record DID and public key in the VDR. Next, the holder generates a ciphertext and stores it in the VDR and receives a push from the issuer. Thirdly, the verifier requests an attribute secret key and verifier receives a key from the issuer. Next, the holder combines voices to generate a VP and presents it to the verifier. And the verifier verifies the VP. Afterwards, the verifier sends an access token to the VDR to receive the ciphertext and decrypt it through the attribute secret key. Then the verifier provides service to the holder. Also, if the verifier wants to revoke, it performs a revoke request to the issuer. The issuer then updates the user list with information about the verifier to perform revocation. This is in second phase of a detailed scenario. First, the issuer generates public parameters and participants each generates their one DID through the following. And then each transmits DDO to the VDR. And next, the holder generates a ciphertext using the selected attributes. Here, a constant size ciphertext that is not affected by the number of attributes is output. And then the issuer generates a EVCH and AVCV. In the key generation, the issuer generates a key based on verifiers attributes. Next, the verifier verifies the VP. And then in the access page, the VDR compares using the VP and the verifier's credentials. Here, the VDR can verify whether the holder has approved access to their data. In the revocation phase, the issuer of here the VDR, the issuer updates the non-spell after comparing the verifiers, credentials, and user list. This is analysis table of proposed scheme. The proposed scheme includes proof value that the holder has approved in the VP and provide revocation through the user list. Lastly, the proposed scheme provides the ability to compress ciphertext to a constant size. In conclusion, the proposed scheme following contributions are as follows. First, verification of holders' data access. Second, deny data access and minimize storage capacity. Through this, the holder's SSI is guaranteed through data access based on DID and CP-ABE in smart vehicles. As a future study, the proposed scheme that can derive tests and performance for application in real environments will be necessary. Thank you for listening to my presentation.